So now in the last lecture, we saw the convolution of L1 functions. And in this video, we're going to talk slightly more on the convolution of measures. Okay, so we want to put some Banach star algebra structure on the measure space. So what I mean by measure is that let's use the notation M of G to be all the, I shouldn't use mu, I reserve mu for the left part measure. Let's just say all the lambda, where lambda is a Radon measure on this G. All right, so because it's a Radon measure, we know we can treat it as a due of the compactly supported of G. By the way, the Radon measure, I should say the complex valued Radon measure. Okay, so we know that this is essentially the due space of the compactly supported function of the G. Okay. So basically, that will put a norm structure on this M of G. So for example, the lambda, the norm of a lambda is essentially just given by the supremum of use the integrate. Okay, so we integrate all the f of d lambda, where your function f is coming from a CC of G, where the sup norm is less than or equals to 1. Okay, so f inside CC of G. Okay. So that put a norm structure on the measures, on the complex measures on G. And another way of doing this is you actually do the decomposition, but because you have a complex measure, you first do it in the real and the complex. So you write this real part and the complex part times the imaginary unit. And then you do the Jordan decomposition. So you decompose as the positive part minus the negative part for each. Okay, so let's say C plus minus C minus, and you do the normal, the total variation. This is essentially add all of them up. Okay, so you do that. All right, then you will get a real valued measure. Okay, that's going to again be Radon. Okay, and you can basically put a norm in this way as well. Okay, so that's basically two way of putting a norm on the M of G. Okay, so our goal in this video is that we now want to put a Banach star algebra structure on the M of G now. Okay, so why do we do that? Well, I guess the motivation is the following. So if you have given L1 function, let's say f is inside L1, well then if you consider M of times d mu, okay, so the mu is the left part measure. So this is going to be inside the M of G. It's going to be a Radon measure, okay? So because of that, well, we have a convolution of the L1 function and want to mimic what we did, and we want to basically define a convolution on a bigger space, the M of G, okay? So this is the goal, okay? So our goal, let me just write it down. I want to put a Banach star algebra structure on the M of G, okay? So that's our goal. All right, so first of all, let's define the convolution. So let's do the convolution. So now I need to have for every, say, lambda and nu inside the M of G, two Radon measures. I want to define what's the convolution measure of these two measures. Okay, so we know the measure, the M of G is the due space. So in order to tell you what the measure is, I essentially just need to tell you how a function integrates respect to this measure. Okay, so let's define the following. So let's say I of f. Okay, so for every f inside CC of G, I want to define some kind of integral so that you can have a bounded linear functional and it corresponds to integrate back to some measure. So this one, I define it as the double integral of the following. So I integrate f of all the xy, where I do the first one inside, say, lambda of x, and I do the second one respect to nu of y, okay? So here because my function is complexly supported, whether I do d lambda or d lambda x, d mu of y first, or d mu of y first and d lambda x next, it doesn't really matter. Okay, so these two I can just rewrite it as d mu of y, d lambda of x. Okay, that order doesn't matter. What matters here is that the lambda one needs to correspond to the first one, okay? And the second one, the new y one, needs to correspond to the second one, okay? So that's where the order matters, okay? So whether you integrate lambda or mu first, that doesn't matter, okay? But the variable, the sequence of the variable does matter, okay? So this one is going to be a linear functional, okay? So why is that? Okay, so if I consider the IF, okay, so I consider its absolute value, so it's going to be less than or equal to, let's say, integrate, let's do the f of xy first, the lambda, and then I do this whole thing, the nu of y, okay, so the first is x, the second is y. Okay, so this is going to be less than or equals to the integral of, because I do the lambda itself, is going to be a functional on the CC of G. So this is bounded above by the infinity norm of f times the norm of this lambda. And then I do the d nu of y. And this whole thing is going to be less than or equals to the infinity norm times the lambda times the nu, okay? And so because of that, I know this is a bounded linear functional. Well, it's linear is pretty clear. So what we have is that there exists a unique Radan measure. Let's call it the convolution. Okay, so there exists a unique Radan measure. Let's call it lambda convolute with nu, so that the I function is given by this integral. Okay, so the integral of f respect to this convolution measure, that's equals to the I of f. Okay, so this is our definition. And because from our computation, we basically just see immediately that the norm of this convolution is bounded above by this part. Okay, so the product of their norm. Okay, so immediately we already have that this is going to looks like a Banach algebra structure. Okay. So of course we need to show that this convolution is going to be associative. All right, so let's do the following proposition. Okay, so here's the proposition. So I want to show that if you say convolute, say lambda with respect to nu, and then you want to do the rho, that's going to be equals to you do the nu and rho first. All right, so in other words, this is an associative convolution. Okay, so let's prove it. All right, so to prove this fact, if I just integrate basically f with respect to the first one, let's say the first measure, you do the lambda and nu first, and then you do rho. Okay, let's see what happens. So we'll just write down the definition. So this is integrate. Okay, so you integrate the f, well, it's a double integral of f of xy. And what matters is that the x corresponds to your first measure. So you have a lambda times nu on x, say on x. And then you do the integrate respect to rho on y, okay? All right, so now the middle one, again, you treat it as a function of x, you pretend y is a constant, so you can break down that again. So this is the integral. Actually now a triple integral of, you break the x as, let's say, x and z, where you do the integral of lambda, well, y needs to be here as well. So the lambda goes to the first variable, which is x, nu goes to the second variable, which is z, and rho goes to the last one, which is y, okay? So you do the integral like that. And now you just replace, you do the change of integration. So because f is compactly supported, you do the Fubini. So let's integrate the last two first. Okay, so this is the integral of, let's say, triple integral of f, x, z, y. And then what you do is you do the d nu z first, and then d rho of y. And this whole thing you integrate with respect to d lambda of x, okay? So now what you have is that the middle one now becomes the integral of these f of the y, the z and y will merge together. Let's call it y again. So fxy, d of the convolution of new and row, evaluate y, okay? And then you do the d lambda x. All right, so again, here the sequence of the measure is not important, but because your x comes first and your y comes second, so this one is going to be equals to the integral of the fx d lambda first, and then you convolute with the new convolute with rho, okay? So this finished the proof, okay? So when you integrate which order you do the star operation, you do the convolution, that doesn't really matter, okay? So you have an associative thing. All right, so I want to do a little one more thing. So this is another interesting one. So if you just recall it, let's say delta of A to be the Dirac measure, basically a point mass at a point A. And of course, Dirac measure, you can see this, convince yourself is going to be a Radan measure. It's fairly simple. In fact, what you have is when you convolute two Dirac measures, so let's say delta A and delta B, what you get is equals to delta of AB, okay? So that's basically your the convolution of the Dirac measure is the product of your group operation, okay? All right, so the proof is fairly simple. So you integrate a function respect to the product, okay? So the convolution, so delta A, delta B. By definition, this is just equals to the double integral of the fxy delta ax and let's say d delta ax and d delta b of y, okay? So in your first integral, so if I want to integrate respect to delta of a of x, is essentially just returning the function value at a, okay? So that's quite clear. So this is equals to f of a y, integrate d delta b of y. And similarly, the second one just returns when the function value, when function y takes the value b, so this is f of a b. But this is the integral of f respect to the delta of AB. Okay, so let's finish the proof. All right, so immediately you have the following corollary. Okay, so basically we now prove the this measure space, the M of G, with the convolution is going to be a Banach algebra. Okay, so we already proved that the convolution is associative, and it's fairly simple. You can check yourself. All the other linearity and stuff are satisfied. The joint multiplication, the identity, the Banach algebra, you require the product, the norm of the product is less than or equal to the product norm, and we also check that. So that's kind of clear. It's also going to be a billion if and only if G is a billion. Okay, so M of G is a billion if and only if G is a billion. That basically just follows from the fact that delta A convolute with delta B is equal to delta AB. Okay, so if your MG is a billion, then delta A times delta B is delta B times delta A. So AB has to be equals to BA. Okay, so that's kind of trivial. And finally, the convolution, this M of G is always a unital. Okay, so that's always unital. So just why is that? Well, in fact, the delta E is going to be the identity. Okay, so contrary to the L1 function, so the L1 space, well, your M of G always has a unit. Okay, that's actually quite clear because, well, think about what happens when G is discrete. Okay, when G is discrete, then we saw that basically the function that takes value 1 at the identity, that function is one function that serves as your unit, okay? That actually just corresponds to this Dirac measure point mass at the identity, okay? So that's essentially what happens. So if your G is not discrete, then of course you cannot use that. But your M of G always have this Dirac measure, okay? So that's why it's always there. And let's just quickly prove the last bit because the first two is kind of trivial. So if I want to say integrate a function f respect to say d lambda convolute with delta of e, this is essentially just the double integral of f of xy, and then you do the d lambda of x first, and then you do the d delta of e y. You can put the d delta of e to the first, so let's say this is the integral of f xy, the delta E of y, then you do d lambda of x. And the delta E of y only returns the value when y is equal to E, so this is the integral of always fx, d lambda of x. Okay, so this basically proves when you convolute with the Dirac measure at identity, you get the lambda back. And the other way is really similar. Okay, so you always have an identity here.